So I defined before as temperature temperature as the average kinetic energy of molecules or particles. This is uh and I said that this is pretty much speed of particles. And that was an easy way for me to explain average kinetic energy, but now I feel like I have to go into it a little bit further. So kinetic energy is actually more specifically defined as 1/2 times the mass of the stuff times by its velocity. So bigger the mass, slower the velocity, if the kinetic energy is the same. So if the kinetic energy is the same, bigger the mass, the lower the velocity. So it's kind of like this. If I have a helium atom and I have a argon gas or krypton gas, the particle, it has a small mass, right? Which must have a big velocity to equal 1/2 of the big mass of krypton times by the smaller volume of the krypton. So it's an inverse relationship between the mass and the velocity. But as you can see, if I have both the helium and the krypton at 25 degrees Celsius, they can still have the same kinetic energy as long as the smaller particle is moving slower than the heavier molecule. And when I say velocity, it pretty much means speed, although in physics you're going to hear that it is speed and the direction. But we're not going to get into that so much in this class. So consider velocity to be your speed for the scope of this class. So going back into this slide, I said that the ratio of the rates of the two gases that I have is dependent on the inverse of the proportion of the square root proportions of the masses. So take a look at this. This is R1, the rate of one of the gas, and the mass of 1 is down below, and R2 is down below on the left, and then I have the M2, which is in the numerator on the right. So this is the formula of comparing the diffusion rate of two gases. So let's do an example just to understand what that formula was all about. It says calculate the ratio of the velocity of helium atom to the velocity of oxygen gas. So let's take, for instance, I have helium gas here and oxygen gas. And I'm saying if I have helium gas and oxygen gas, and I'm going to draw oxygen gas as two circles, going through this pinhole into the other side, and into the other side, then which one will diffuse faster? The helium, which is a smaller atom, will diffuse faster. However, how much faster is my question. Okay? So I know from the periodic table, it says He, and down below that it says 4.001, which means that 1 mole of helium is equal to 4.001 gram. And also on the periodic table it says oxygen O2, it says 16.00, pretty much that, grams. And so 1 mole of oxygen, this is just O2 is going to equal 2 times 16.000 grams, which comes out to be 32.00 grams. Okay, and so I know that this is my mass. This is my molar mass. Molar mass, meaning mass of a mole of oxygen, which is 1 mole of oxygen gas now equals 32.00 grams. Okay, so those are my molar masses. But now if I want to compare the rate of helium versus the rate of oxygen, it's going to be the square root of the mass of the oxygen on top. So it has to be 32.000 grams on top. And then the mass of the helium down below, 4.001 grams. So if I were to calculate that, I would get 2.828 as my answer. Grams cancel out. This is a unitless number. In other words, He is 2.828 times faster than O2 when diffusing. Okay? Or they're just faster in their speed. This is our second example of Graham's law, and this is a picture in the middle of a long tube with 2 open ends. In one side, I am going to put ammonia, NH3, in it, and the other side, I'm going to put a cotton ball full of hydrochloric acid. When these two mix, NH3 plus HCl make NH4Cl, and this is a white solid that I want to get. Okay? I want to compare the diffusion of the NH3 and the diffusion of the HCl and see how fast they travel relative to each other and at what point of the tube these two gases are going to meet. So let's first of all find out the mass, the molar mass of NH3. When I say molar mass, I'm talking about the mass of 1 mole of NH3. And looking at the periodic table, it says N, this says 14.00 grams, and so that is going to be 14.00 grams. So I have 1 nitrogen, which is 14.00 grams. My H, I have 3 of them, so it is 3 times 1.01 grams. And if I were to add all that up, I would get 17.03 grams. Over here we have hydrogen, 1 of them, and that is 1.01 grams, and my 1 chlorine is 35.45 grams. So my HCl, 1 mole of HCl, weighs 36.06 grams. So I know that between these two, that the ammonia is going to travel faster. So I'm going to put the rate of NH3 on top and then put the rate of HCl on the bottom, because I want a number that is greater than 1. So HCl will become, I will have a denominator of 1. And now I would know how much faster the NH3 travels in comparison to the HCl. So I'm going to square root this, and that becomes 17.03. Oh, see, this is why my mistake. If I put HCl on the bottom, I need to put in the numerator 36.06 grams, because that is the mass of my HCl. Please remember that it's an inverse proportion. And I'm going to put the 17.03 grams down here. If you want to do the calculation yourself, please try it. Stop the video and try it. Otherwise, I will give you the... And the answer comes out to be 1.45 times. So NH3 travels about 1.5 or about 1.5 times faster than the HCl, meaning because the ammonia travels faster, you're going to see that the ring a white solid of ammonium chloride is going to be closer to the HCl, and it's about 1.5 times, be somewhere around here. Okay. Last idea, which is real gases versus ideal gases. Real gases differ most from ideal gases at low temperature and high pressure because at low pressure and at low temperature and high pressure, gases are closer together and they begin sticking to each other and condensing into a liquid. So remember that we assumed in ideal gas law that these gas particles will have no attraction or repulsion towards each other, but both of these, repulsion as well as attraction, happens in real gases, and when they do happen, when they get really close enough and they're moving at a low speed, they end up sticking to each other and becoming a liquid. And that is why in this picture you have pressure as my x-axis and PV over RT over as my x-axis, and you can see that at high pressure the real gases sway from the ideal gas line.